Hey, Asim.
Yeah, hi Alex.
Good to see you.
Yeah, same here.
All right, no issues getting set up, I see.
So just let me know, Alex, when I should start.
Uh, I think we're live. Okay, here we go. All right, so let me do a little introduction. Let me make the screen big. Okay, welcome everyone to Neuro-Symbolic Wednesdays. So, if you've caught the beginning, if you haven't missed much. This is the third installment, and thanks for bearing with us. Last time, we think there was a glitch in Luma had to do with Cloudflare, so we weren't able to do it that week. And then there was Thanksgiving, but now we're back, and we're lucky to have Asim, who will talk to us about training large reasoning models. So this will be have a tutorial aspect to it. So it's very good here at this point in the sequence. We started with Abu, for those of you who caught that, who told us about some of his deep experiments around the reasoning capabilities of large language models. And so natural follow-up is to go deeper into how the so-called reasoning models really work, how you train them, and Asim will take us through that. Here's a little bit about Asim. So, extremely accomplished at IBM Research, and I know that because, and many of you who've been following us over the years know Asim helped me lead the Neuro-Symbolic AI effort, global effort at IBM when that was going on. And many of you have interacted with him in the community. So it's a pleasure to have him here today. And all these slides will put out, by the way, on Discord. Just a little preview. Next week, we'll actually, and after these first few talks where we're starting kind of neuro, since many of you are coming from that base of knowledge, it'll be a nice setup for kind of that motivates Neuro-Symbolic AI. And who better than to give that intro than Louis Lam, one of our pioneers in the area. So that'll be next Wednesday. And for those of you who have not connected with us in all the different ways you can connect with us, so here are some of the ways. So, and take a picture of this or whatever. But Discord, if you have to pick one, the sort of center of everything is Discord. That's where you can find out anything. That's where the community is interacting. Our GitHub is where a lot of our work will appear and has started to appear. And then, of course, YouTube and LinkedIn. The learning site we mentioned last time is under development and almost there. So you'll be seeing that pretty soon. And that's where you'll want to go when you have questions like, what is logic anyway? And what do you exactly mean by reasoning? And so on. We're going to have all of our past videos there, including all the tutorials over 4 years or so of summer schools and other events. Okay, and I'm giving it a few minutes so that give people time to join. So I'll just mention uh, while we're waiting for people to join, this project is something we've started working on, and we're looking for any members of the community who want to help. This is sort of, you could say, Neuro-Symbolic AI's answer to the Agentic protocol. Okay, you can see here the link to go to. You can email me. You can email Can Mingir, who is you'll always find on Discord. And he's leading this project, and this is we're designing a fairly sophisticated system, and we're looking for that involves a language aspect, programming language aspect, systems aspect. So anyone who has interest and experience from those kinds of areas in particular, please reach out. And you can read more about it here. Okay. Oh, and maybe I've given it enough time. Maybe we shouldn't kill more time. But maybe next time I'll reiterate a little bit about some of our projects and other ways to get involved. We are hiring. But that's it. Maybe now I'll hand it over to Asim.
Thank you, Alex, for the introduction. Thank you for the invitation also. Um, so let me share my slide. Okay, I hope you can see it in full screen mode.
I think it looks good. Yeah.
Okay, great. Thank you. So I'll be talking about what we now call large reasoning models, how they're a bit different from large language models, and I'll focus on DeepSeek R1, how it was trained, what lessons can we learn from that, but also talk about reasoning in general in context of large language models too. So I believe that reasoning, the definition of reasoning was redefined after large language models came into the picture. And then we went to large reasoning model, which we very commonly use and maybe sometime unknowingly are using on Gemini, OpenAI, or other platforms. And then I'll talk about DeepSeek R1 and what is beyond. Um, what I will not be doing is that whatever I say is not a final verdict. So it's an evolving topic. Whether inference time scaling is good, bad, required, not required, all of that is still evolving and it keeps changing. So very often we see a paper that conflicts with the earlier paper, and that's fine. That's how research works. And I'll not overanalyze LLM failures also. We understand what LLMs are capable of, what they're not good at. So I'll keep it balanced. So first of all, like starting when we say reasoning with LLMs, as I said, in my opinion, the definition has been redefined. There are two kinds of reasoning. One is like natural language reasoning, the kind of reasoning that humans do when we ask them something, and there is formal reasoning, which needs formal solvers like prover 9, prologue, that kind of first order logic, or something like some symbolic representation. So when we talk about large language model, we mainly talk about natural language reasoning. We try to do formal reasoning with them, but we cannot expect them to be as good as the symbolic reasoners. They cannot provide us any guarantees there. Uh, and reasoning is a process of thinking about something in a systematic way. And reasoning compares with retrieval, which is just extraction from the previous experiences that we have and that are there in the memory. Of course, large language models don't do exact retrieval like search. So they retrieve something from their memory, they rewrite it in a very natural looking very nice way, and that's what we like about large language models. So according to Professor Rao, whatever LLMs do, it's basically information retrieval. They appear to reason, but it's again sophisticated pattern matching. Another differentiation, in my opinion, when we talk about reasoning and other natural language tasks, with natural language tasks, we can have suboptimal solution also. For example, if I ask LLM to write an email for me, it can either do a fantastic job or just average job. And usually we don't care so much as long as it's well structured, everything is there. On the other hand, with reasoning, we usually want 100% reliability. Okay, otherwise it kind of is not very useful for us. We need to verify everything. Okay, and just to understand it better, um, what if I give you a calculator that is 80% of the time correct? Okay, so it's pretty much useless, right? You have to verify everything it says. It can be 80%, it will take a lot of time. Okay, now what if I come up with a new calculator that is 90% of the time correct? Again, the problem remains the same, right? So in my opinion, reasoning have this kind of problem where other natural language tasks does not. They can do average performance. Reasoning, on the other hand, needs to be 100 or at least very close to 100 and verifiable. Also, various ways to think about large language models. One of them is system one, system two kind of thinking. System one is intuitive thinking, where we do not have to put much effort. It's a lot like memorization, not reasoning. It's like identify a scene, that is system one task. um, Driving, if you are a good driver, you're used to driving, it can be system one task. On the other hand, if you're a new driver, it can be system two task. You have to put explicit effort into thinking what should be your next step, right? So system 2 is usually a task that is slow. You have to put intentional effort. There are some constraints that you need to reason about consistently. For example, planning a vacation is clearly system 2 task. You need to ask where, who is going, what are the preferences, what is the budget, and so on and so forth, right? In real life, we need both system 1 and system 2 tasks. So nowadays, what do we do when we need something? We ask uh, like these LLM models. So I asked OpenAI model to create an image that needs both system 1 and system 2 tasks, and this is what it came up with. Okay. um, a person driving solving a math. So we can already see the problem with this image, right? So the reasoning issues with LLM, like, it's already very clear. This should never happen. You should not be doing math in this way while driving. You should be looking on the road. I don't know where this person is going. So a lot of problems already there in this image, right? Yet another way to think about it is like induction, deduction, abduction, kind of what are LLMs actually doing. uh, so LLMs are basically induction machine. They have seen a lot of data during pre-training, post-training, alignment, and so on. Induction is where it sees a lot of example and it makes a generalized assumption about that. So it saw, for example, Socrates died, Plato died, Aristotle died, and it generalized it to, oh, okay, all humans die. Okay. Deduction, which large language models can do during in context learning, when we can give it some rules and then it can come up with some conclusion. It tend to do that. So but again, like, always keep in mind, the large language models are all their learning comes from the biases they have acquired during the pre-training and post-training phase. Okay, so even in context learning, those biases don't go away. And abduction, inferring the most probabilistic explanation. This is what inference time scaling tend to do. Okay. For example, if the observation is Socrates is human, Socrates died, it can come up with hypothesis, okay, probably all humans die. So this is the best explanation based on whatever it has seen. But the fact that LLMs primarily are inductive reasoning machines, we should always keep that in mind. And expecting them to do deduction reliability, abduction reliably is can be dangerous. Okay. So this brings us to large reasoning models, which tend to do abduction. So this is a prompt that I asked. I have two bananas in the room. One fell down. How many bananas are left in the room? It's a simple question. There should still be two bananas in the room. Um, so this is what it does. It takes a long time. It takes thinks kind of thinks. In different ways. It can assume, it tends to assume that, okay, this might be a trick question. What happens if the banana falls down? And ultimately, it comes up with the right answer. Strangely enough, this simple question, when I asked other models in the middle of this year, okay, early this year, Gemini got it wrong, OpenAI GPT-4o got it wrong, and Copilot got it wrong. Okay. So, but when I asked it to Quen 32 billion reasoning model at the start of this year, it got it correct. And this is the output. In large language model, we are if we compare large language models and large reasoning model, the underlying mechanism is very similar. What we expect in large language model, we are mostly looking at next tokens. In large reasoning model, we are thinking in terms of chain of thoughts. We can say that large language models are system one, large reasoning models are system two, because they take more time at inference. They tend to put explicit effort there. Uh, of course, when I use the term thinking, it's not the way humans think. So please take it with a grain of salt. Um, and we know the famous models. These slides might be a bit older, so there are newer models available now. But OpenAI made the first successful demonstration of LRM with O1 models, and then DeepSeek, R1, Quen, all these models made it very famous. So, and this is taken from OpenAI blog that was published with the O1 in 2024 October kind of time frame. So we see that test time compute or inference time compute does make sense. Either train the model, take a lot of time during training, train the model much better on more tokens, on better data and stuff, or give it more time at the inference stage. So this is log scale. So given more time at inference, usually the accuracy keep on increasing. And is this entirely new? No, I'll show you that this is not entirely new. We were doing it before O1 also. So, but this is a trade-off between train. So this shows, in order to keep a performance in a specific board game, this is a trade-off between train time and test time that you have to maintain in order to get some result. Okay. Uh, so as I said, we were doing inference time compute even before O1. O1 just made it very efficient. For example, we used to do simple prompting. We used to do chain of thought where we come up with intermediate steps, and self-consistency. Self-consistency is actually one of the best inference time scaling methods even available today, but it's just very inefficient. We do a lot of chain of thoughts, up to 50, sometimes even more, and we select we do a majority voting. We select the answers that are most probable, and that give us our solution. As I said, this is inference time scaling, but it's very inefficient. What if we have verifiers? If we have verifiers to evaluate our outcomes, which for example, we have trained verifiers in terms of reward models, outcome reward models or process reward models. What we can do is, now we can check our question and solution pair, and we can come up with how good the question and solution are. If we have trained verifiers available, we can do more. We can do a tree of thought kind of approach, where we kind of branch and we figure out if the step is in the right direction or not. We can backtrack, we can take another branch, and so on and so forth. We can do best of n. We can do Monte Carlo rollouts from one node and see how many time it succeed or fails. So we can do a little bit more exotic stuff once we have verifiers available, trained verifier like reward models available, or LLM as a judge in some cases also works fine. And the task of these large reasoning models is just to, no matter how the data was created, whether it was through supervised fine tuning or reinforcement learning, alignment, whatever, it just needs to increase the likelihood of good answers versus the bad answers. So instead of taking instead of, for example, doing self consistency check, running a lot of different chain of thoughts, or taking a chain of thought that is more exotic and it can do self correction, here we just take one path and we try to increase the maximum likelihood probability of that, maximum likelihood of that answer. So that's what we are training in the large reasoning models. And this is a combinatorially hard problem, so it's not trivial. And DeepSeek, this brings us to DeepSeek and why DeepSeek created so much hype. I always say this is a technical perspective. It has nothing to do with how the, the market responded to this news, which was very strange for me. Uh, but what DeepSeek did, and there were, other than OpenAI O1, also there were Quen models already available before DeepSeek came into picture. But what made DeepSeek so different was some of the things that are listed here. It was first open source, full pipeline for building reasoning model. Um, O1 did not open source it, Quen did not open source, a few others did not open source what they were doing. But DeepSeek R1 decided to open source that, and it got them a lot of traction. They open sourced the model weights, which was amazing. So this was the first open reasoning model that of that size that you can play with. They open sourced many distilled models out of it, Quen, Llama, different size models, even very small models. And it actually, when you look at DeepSeek R1, you realize that the innovation did not start with DeepSeek R1 paper. There were several series of very good papers from DeepSeek, that people kind of missed in 2024, 2023 even, that were pointing towards low hardware usage, efficient algorithms, and especially in alignment and low cost. Few things that they did not do, they did not open source the data. That was kind of sad, but it's understandable. And secondly, they did not talk about the money spent on iteration before the final run. So they did talk about the cost of the final run, but they did not talk about how much iterations they did and some of the learning they got from those iterations. So low training cost was one of the thing, and it cost 6 million for the final run, but the actual cost is not known. As we all know, it's not about the final run only. There are a lot of iteration leading up to that, and most of that 6 million goes to pre-training phase anyway. Okay. Uh, and there were some rumors that they have distilled the data from OpenAI O models, but I don't know. Some people still think it's true, but the O1 does not share the thinking process with the user, so I don't know how useful it will be. So what's so special about DeepSeek R1? And to understand that, first we need to look at what they did with DeepSeek V2 and V3. DeepSeek V3 is the base model they started with for DeepSeek R1, which is a reasoning model. And DeepSeek V2 and V3 are chat models. They are 671 billion mixture of expert model, 37 billion activated parameters for each token, which makes them quite efficient. And these are base model for R1. And some of the innovations they had in those models are GRPO, then they had MLA, a multi-head latent attention, some reward functions, and auxiliary loss-free load balancing, and few others. I'll discuss some of them. And then they also did some hardware tricks where they used lower precision. They used some communication, compute interleaving in GPUs to make it more efficient in terms of memory and compute usage. So in terms of mixture of experts, we know that mixture of experts is a very good way of having bigger models that can run very efficiently at inference time. Um, they are not always easy to train. So in this case, they had 600 billion model, 37 billion active parameters. So they had two kind of like they had a router and few of the fixed experts that everyone shares, and few rooted experts that were dependent on the input tokens. So this model that they introduced was one of the innovation they had shared in the earlier paper. Another one was auxiliary loss-free load balancing. Here they had a dynamic bias term for each of these experts that made sure that all the experts are used almost evenly, and one expert is not doing most of the job. And this was better than the load balancing term that people usually all add in the loss function. Multi-head latent attention. This is a way to compress the KV cache. We know that most of the memory for each token that goes in the computation of the output goes to the KV cache for each token. So they compress the KV cache, and they projected it when during the inference compute, which is much more efficient than keeping the full size cache for all the tokens. So this also was published in their previous paper. Multi-token prediction, instead of predicting one token, they were predicting several tokens into the future, which helps during the training to create better reasoning chains, and also it helps during inference time to kind of have a speculative decoding that they utilize. Okay, so all these innovations made DeepSeek V3 a very good chat model, which did not get a lot of attention. And then came DeepSeek R1. It got a lot of its performance gain because of what was done on V3, not what was done for R1 model. So I'll discuss briefly what R1 is doing, and I made this figure to show you all the steps that are going on and what it takes to convert a chat model into a reasoning model. So we start with DeepSeek V3, and they fine-tuned it with thousands. So please bear with me. They shared these numbers, they shared some information, but as I said, they don't share the exact data. So we cannot be 100% sure what are the exact number, what kind of data they're using. But this is the extent of the information they have shared. So at the first stage, they fine-tune the DeepSeek V3 on thousands of human curated long chain of thought examples. Uh, they have tried another model which they call DeepSeek R10, and they don't start with fine tuning for that model. And DeepSeek R10, they found the model to be good at reasoning but bad at other natural language tasks. So then they introduced the first fine tuning stage, which you can see here. The second stage is rule-based uh, uh, reinforcement learning, which is another innovation they did called GRPO algorithm. I'll discuss that later. And in the first stage, they use rule-based rewards. Rule-based rewards, for example, if the syntax is not correct, if the answer, because they were doing math and code, they can match the answers. If the answer is not matching, they give it a bad reward. If the answers are matching, format is correct, they give it a good reward. So they used around 144K math and code examples here to train the model. So here the model become very, very strong in reasoning, but it loses some of its general capabilities, which are natural language capabilities in question answering and summarization and translation, this kind of task. So here they again, first of all, they distill the model. They have around 600K very good quality reasoning traces, and they added 200K new non-reasoning examples. And here they use two rewards in the next RL stage. They again do GRPO. Here they do rule-based for math and code, and reward model for non-reasoning tasks, natural language tasks. And this gives us the DeepSeek R1 that we have now. And these traces that they got from their reasoning model, they also distilled it into Quen of different sizes and Llama model of different sizes. And they also released this distilled R1 models. So in cold start, what they did is they start with V3 base. They give basic reasoning capabilities from the long chain of thought that were created by human. And this is about DeepSeek R10, where they did not use, they directly start with RL. They did not have the cold start. And that had some issues in natural language capabilities. GRPO, another innovation that came from DeepSeek math paper in April 2024. So it was much earlier, like almost a year earlier than DeepSeek R1 paper, or 9-10 months earlier. Here, what they do is instead of creating a single or a pair of samples for rejection, they create like up to 64 samples per training example when they're doing reinforcement learning. Then they score according to some rule or according to reward model. And then for each sample, they have a mean of all the outputs that they got. They select the best one, they select the worst one, they create many pairs. And instead of doing one update for one sample, they do multiple update, because now they have like up to 64 sample and they can create many pairs, combining the best and the bad example. As we understand in reinforcement learning, we do need a reward model. So if the reward model is not good and we don't get good rewards, then of course this stage will be a problem. But because they're mostly relying on code and math problem for reasoning capabilities, they have the final answer they can use to verify. Similarly, the syntax that they want for code is very clear. If the code does not run, then the code is wrong. Okay, so they were able to exploit that fact also. Rule-based reward, so as I said, so this is the kind of prompt that they give. If you see here, the reasoning process answers are enclosed within think and think tokens, answer and answer tags, and so on. So if these tags are missing, then again it creates a format problem and you give it a very low reward. Same goes for accuracy rewards. If the answer does not match, you give it a bad reward. Yeah. Rejection sampling. This is what they did with the data that they sampled from their earlier reasoning model, and they did the second stage of fine tuning and second stage of reinforcement learning. And after the first stage of GRPO, they said that the model became good at reasoning, but they lost some natural language capability. So they had to rebake those capabilities into the model. And then comes RL stage 2, which is basically symbolic reward plus the reward model that they had trained for helpfulness and harmlessness on their data. And these are the results. The results don't matter a lot right now because there are newer models that are much better at the capabilities. But this talk is more about um, the process with which we can think of making a reasoning model. Later, after DeepSeek R1 paper, this is another interesting paper that came along. There are many more that we can talk about, but this is a very easy to understand paper where they curated a small data set. They first created 50 or 60,000 data, and they selected like the best 1,000 question answer pair, and they did a little bit of fine tuning, and they converted a model um, into a good test test time scaling model or reasoning model. Okay, so the message uh, of this paper basically is that quality is a lot more important than quantity. So it's not about creating million examples or run reinforcement learning for a long time. It's mainly about the quality of the data. Of course, they are using few more tricks here. For example, they are using budget enforcing. In budget enforcing, what they do is if they think that the model is using too many token, it can just ask the model to stop. And if they think the model is trying to answer too quickly, they can ask the model to keep thinking. So they are doing some budget forcing also. But overall, this paper showed that the quality is a lot more important, instead of talking about how many million or um, how much data is required, whether human curated or not. And does reasoning models solve all the problems we had before? So the answer is no. They still suffer from the issues that we saw with older models. Maybe a little bit better than them, but still. For example, in GSM 8K, which we are all familiar with, it's a word problem arithmetic task. Um, just like this, Sarah has 15 red marbles and 25 blue. So it's simple. Like I believe maybe middle school level questions. Um, so, state of the art models get 95 to 98% on GSM 8K, but there are other data sets called GSM hard, GSM symbolic, which makes the problem much more difficult by adding several variations, several templates, bigger numbers, and so on and so forth. So there is a GSM no op data where what they do is they add an extra instruction into the question that has nothing to do with the original question, so it should just be ignored. But if you see on the right hand side, almost all the models get significantly affected by that extra instruction that should just be ignored. Okay, up to 65% decline in performance. But even if you look at the top O1 preview, O1 mini, those models still get affected uh, by this no up instruction. Okay, so it takes extra time, but it does not mean that it solves all the problem. And then there are this kind of papers also. So reasoning model don't always say what they think. Chain of thought reasoning in the wild is not always faithful. And the few learnings from these papers are that LRMs generate visible traces, but they are not actual internal reasoning. So they're more about showing, not about actual reasoning. And even though the accuracy of final answer keeps increasing if we give longer chain of thought or longer time for inference, it does not mean that the reasoning quality becomes better. Okay, models can reach the correct answer more often when we give longer time, but the traces can still be incorrect or misleading. So we should keep in mind, these are some interesting reads also, and very recent if you want to check them. This I will skip. So reasoning, yeah, we started discussing reasoning in terms of like emergent properties of large language model back in 2023, kind of. And then came O1, R1. There are recent papers that basically share the data also. So if you ever want to look into that, now they share the full recipe, plus even sometimes the source code, plus all the data they have used. So it's becoming pretty amazing. And then I believe the in future hybrid neurosymbolic plus verified reasoning is where we are going right now. And in a way, I understand that agents might not exactly be doing that, but agents provide us a way to go there. um, just instead of just mimicking some pattern, mimicking the pattern of reasoning, doing real provable reasoning. So agents help us combine this neural and symbolic part very efficiently. So maybe this is the direction we should be looking into. So in this case, we can use what LLMs are good at. They are good at creating hypotheses, abstractions, translations, format conversions, and so on, and symbolic for verification, um, handling constraints, and so on and so forth. Um, and then, as we know, that agents have usually validators, verifiers, which can continue or which can reflect on its own output until we reach some level of proof or correctness that the agent is satisfied with. So this is a question mark whether agents is the right direction. And then this is the last slide. So DeepSeek R1 got a lot of hype because it was the first model to publish details of how reasoning pipeline works, or how you can build your own reasoning pipeline. We know for a fact that some of the even big players in the industry may started making war rooms to replicate what the DeepSeek R1 has done. So it was a big thing. It still is. Um, One thing that the message here is that algorithmic innovations always win over brute force approach, and that's what people missed before the R1 paper was published. There were series of papers before. For example, even the DeepSeek math paper was published in April 2024, but did not get a lot of traction. So there are very cool algorithmic innovations going on along with the brute force approach that we can see clearly winning in the short while. Okay. And another thing that they showed is that on smaller model, it doesn't always make sense to use the same approach that we use to train bigger models. So having a strong teacher model is much better, um, because we can distill from the teacher and we can train smaller RL models. So it's not feasible to train RL models, small RL models with a lot of reasoning data, with a lot of long chain of thought, GRPO, the same way that they did for R1 DeepSeek. Okay. Uh, yeah, and that's it. Thank you. We can take some question answers.
Okay. Well, thanks, Asim. Great
You.
stuff. I think a lot of people have been in both neurosymbolic and especially in pure neuro have really wanted to understand what actually happened in the DeepSeek event. So we have some questions. I have a bunch of questions, but let's go to the audience. So what is reward hacking? Why not use a neural model for the reward?
So first of all, reward hacking is where the example that come to my mind a few years back, there was a computer vision model that was giving very good results, classifying wolves from husky dogs. Okay, and when we looked at the attention, the researcher figured out that it was not looking at the animal at all. It was just looking at the background. If the background was snow, it labeled it as wolf. If the background was not snow, it labeled it a husky dog. So So that is kind of hacking that reward model. There can be some clues in the data that we as human miss, but the model picks them up. Okay, so if the reward model has if their goal is to get maximum reward, so let's suppose if you give the right answer you get one reward. What if you give reward what if you get right answer two or three times? Maybe the reward model will give you double or three times the reward. So these models just learn to just keep repeating the answer and get maximum reward, but that's not what we want, right? So that is reward hacking. And when it comes to neural reward, of course we are doing, reward models are all neural, so we are doing and recently we saw, not very recent, but process reward models that can give some reward, very dense reward even to each step, um, are becoming very useful for many approaches like star and beyond. So we do use neural reward model all the time.
Great. A comment. I don't know if we can easily attach reasoning techniques like chain of thought to diffusion-based LLMs.
That I don't really know. I don't know too much about diffusion models, so I'll be happy if someone else want to chime in here. But I don't think so. Again, the problem remains the same. Like these are induction models, right? So I don't LLMs are not doing anything that other models should not be able to do. Okay. So I don't see any reason why they should not be able to do the same thing that LLMs are doing.
Okay. Um, yeah, I mean, my quick comment on that is it seems like a lot of these tactics sort of are irrespective of the architecture itself.
Right.
So um, the speaker also mentioned in the beginning the different ways of reasoning, deductive, inductive, and abductive, and also mentioned that LLMs today are like good inductive reasoners with chain of thought, if I understood it correctly. Is it right to assume that to achieve higher scores, newer models need to be trained better in other reasoning modalities where they perform worse, like abduction?
In other modalities.
I guess meaning the other kinds of reasoning where more improvement is needed.
Yeah, maybe, but again, like, it comes again to the way we train these models. Um, Most of the learning, if you look at the models, most of the learning comes from pre-training anyways. Okay. And then in my understanding, pre-training is giving most of the knowledge to the model. Post-training is just giving the kind of syntax and structure, and RL is giving a bit of generalization to the model. Okay, so if we can add more modalities, more data, then it will improve, it will tend to improve. But again, um, it can be more like even benchmark hacking in some sense, that it will improve on abduction, it might decrease the performance on some other benchmarks.
Maybe you can comment on that, Asim. I mean, I've heard many people comment on the state of LLM work. That it seems like it's really these things are chasing benchmarks rather than performance, rather than foundational, changes. So, you want to any remarks on that?
So, in terms of that, that's a very good point, Alex. And if we look at our favorite benchmark in AI, MNIST benchmark, everyone is familiar. It took a decade and a half for people to reach human performance on MNIST benchmark. Okay. On the other hand, nowadays it take, if a benchmark become famous, it takes someone 1 month or less to hack that benchmark. Okay, so there, I don't say that they train on that benchmark, but these LLMs make benchmark hacking very easy, and we should not get into traps. So that's another reason why I almost don't want to share any numbers in my slides, Alex. I think it's no, there is no point now to share those numbers. So that's what we should keep in mind, not to get impressed if something is giving good numbers on some benchmark. And if you want to see more, please look at some articles about llama 4. um, you will understand that why this can be very dangerous also.
Can you say more about that? Do you mean you don't want to share numbers because they'll be instantly out of date within?
They will be, first of
Mhm.
all, they'll be instantly out of date. Secondly, if you find a benchmark, a model that is doing very good on one, for example, agentic benchmark, when you start using it, it completely fails on your own problem. Okay. It
Mm.
does not reflect, it does not generalize on your own problem. It's generalizing to the existing benchmarks, but it does not generalize to your own problem. Another thing that recently OpenAI researchers showed in a paper where they mentioned hallucination. Why do models hallucinate? Um, our evaluation also have problems because we are many times, um, one example that they give is we are many time evaluating the models on multiple choice questions. So in multiple choice questions, we are telling the models that if you don't know, make a wrong choice, you still have 25% probability of picking the right answer, right? So we are telling them to kind of hallucinate and come up with the wrong answers. So in the domain that they are trained on, in the domain where the benchmark lies, they seem to do very well. But as soon as you go to a different domain, they are as good as whatever was available before them.
Hmm.
So that is the issue we see
Uh,
very often.
you think this multiple? Are you saying this multiple choice thing is maybe the cause of why people have reported that the reasoning models give more hallucinations?
This can be one cause, and secondly, Alex, we are giving them more time to hallucinate. Also, we are giving them more token budget. And for example, in the S1 paper that I showed, they're actually telling the model to not stop here, continue. Okay. So when you're asking the model to continue, you are kind of asking the model to think in various direction that can be very far from what it actually needs to say, right? So yeah, so that's why I believe one of the reason is the evaluation, other is the just extra token, extra budget we are giving them.
Uh, are,
And
are you sort of saying like because we're asking it to uh, search different search paths, it's sort of because it's not really understanding those search paths as potentially throwaway. It it sort of starts to think they're real.
they're real. So for example, I asked a model, what is 2 plus 2, explain to me, and it immediately said it's 4, but most probably this is a trick question. And then it went in strange directions. Okay. It went to riddle solving and very complex theories about what the question could mean. So um, yeah, so
There's a really funny YouTube video that I watched about a guy who gets into he sort of uh, projects his delusion about how he was born the smartest baby of his year on in the world, and it keeps because he plays along with the delusion. With it kind of makes the LM keep going more and more down this rabbit hole, and it,
yeah. Yeah, these are very, especially when I see this kind of video, Alex, I'm really afraid what effect it has on children using it. So it seems very dangerous to me.
Another question. I heard DeepSeek R1 benefited a lot from the work that was done for DeepSeek Math, which came out much earlier in the year but didn't get much attention. What did DeepSeek Math contribute?
DeepSeek Math contributed the GRPO algorithm. That's the most common algorithm being used these days. And if you look at PPO algorithm, so in PPO, what happens is that we Of course, given that we have a nice reward model, or we have a nice symbolic reward, what PPO was doing is that gets a query, it generates few probable answers, and it picks the one that is most probable. Okay, it picks one, or it picks a pair. And people were also using DPO before that. But GRPO, what GRPO is doing is that it, instead of picking just one and make one update for one query, it gets 64, up to 64 possible answers for that question. And then it very cleverly selects various pairs out of it, and it makes several updates to your weights, which makes it very efficient.
Okay. Why do the large reasoning models and well, what does their answer quality grow with long inference time? Since reasoning in those kinds of models is essentially a hidden part of the output, is there any understanding on the reasons behind that?
So first of all, why do performance increase with chain of thought anyways? Okay. So, and the reason for that is, I should have added some example. The reason for that is that large language models don't know what the final answer is before they start talking. Okay. So they just know what the next probable token should be. So there was a famous example in a paper where they ask, what is the largest state bordering Mississippi River? Okay. So if I ask anyone, any person, even, they will just come up with some state that they know is next to Mississippi River. But if you if you ask the model to do a chain of thought, it will first list all the states that are bordering Mississippi River. Then it will fetch, if it can retrieve, or if from its memory it will retrieve the area of all those states, and then it will come up with the final answer. So now it can see a lot more that was not available to it. So all the numbers are available, all the states are available. So now it can make a much more informed decision when it comes with the answer. So, and the same is true if you give it more budget for more thinking, fetching more facts, making self correction if it made a wrong assumption. Basically, we expect the model to do better. So it's similar to self consistency, and also if you are running multiple chain of thoughts, we expect the model to do better. So it's just about fetching more from its memory before answering.
Mm-hmm. So just a general comment related to that. So when you presented these detailed tactics that are being used to improve these large reasoning models, or even what sets them apart from the regular models, it strikes me that very little of it is reasoning specific. It's actually just be more careful kind of, but that be more careful you could do with any kind of query, not necessarily a formal reasoning type of query. So is that the case? Well, and which of them are actually reasoning specific? I mean, when what you proposed as a direction, which is the verifier, let's say, I think what you mean, if I translate you right, is let's say the verifier is a formal reasoner that's guaranteed correct, then that's reasoning specific. but otherwise, are any of these things really reasoning specific?
No, so that's a very good point, Alex. And the thing here is, what people do is, and that's another issue with benchmarks, that many benchmarks are about math and code. Okay. So, and the reason why people do math and code is they're easily verifiable. There is a lot of data available on these two domains. At least a lot of question answer pairs available on math, a lot of codes available on coding. So all they did was, in order to improve reasoning, was they focused on math and code basically. Okay. And it seems to generalize to other reasoning domain also, where math is not directly involved. So, and no one is checking whether the reasoning traces are good or not. if they come up with the right answer, they assume that the reasoning traces are correct. So that's how they're taking it.
So yes, this is, I think, a very important point, is we can expect a struggle or even very slow or non-progress in areas where it is difficult to have ground truth, because
We
the
yeah,
essential basis of a learning scheme.
definitely, yeah, that can be a big problem.
And just on that, it would seem to me then that these various ways of being careful, as I put it, and they're, I'm wondering which of them uh, has the biggest bang for the buck. Which of these innovations kind of seems to have provided the most?
They mention it in the paper, and they mention the GRPO, the RL part is the main part that introduced this kind of uh, so-called thinking in their model. So it improved over time itself. So that's what they say. But
And
if you go, yeah,
go ahead.
I was just saying that if you look at some other papers, they kind of contradict also. They say fine tuning is more important, but it's yeah.
And what about, but at least one part of it is, that's reasoning specific actually, is the data set, of whatever, 1,000
Yeah.
question answer pairs that
Yes.
are reasoning oriented. So how important is that?
So that we can look at the S1 paper for, and that's the exactly reason why I added S1 paper. They mentioned clearly that a good quality 1,000 examples, carefully curated long chain of thought can make or break the model. So
Aha.
it's very important. So,
So,
and DeepSeek R1 paper, as I said, so DeepSeek, they tried without the cold start, DeepSeek R1 0, and they said it was good at reasoning, but it was mixing up languages. It was mixing up Chinese and English language. It was mixing up some other stuff, and it lost a lot of its abilities that it had before. So
and what is the reason for this? Th- this this uh, uh, you know would seem unfortunate that you sort of can't have everything. There's a trade-off
okay.
between NLP performance and uh, reasoning or something. But why is
No, so they say that they recovered that performance
that?
when they trained again on some data. Um, so, but anyways, the ideally what we always do is that if we are training on our own data set, also we usually keep a replay buffer of the general trends, general traits that the model had. So I believe if you just train on one specific data over time, it will just start overfitting to your data. It will start forgetting previous skills.
Hmm. Yeah, I think people personally are not talking about that enough, that the finite sort of capacity means as you get better at something, something else has to go.
Something else has to. So that's another. So the more you fine tune it for a few benchmarks, the more it get overfitted to not a single benchmark but multiple benchmarks now. Okay, and when you try to apply them outside those benchmarks, you find that okay, the jump was not that big. uh, it seems very big on the benchmark, but it was not very big outside those benchmarks.
Um, Very good. Back to some questions here from the audience. So, uh, provided someone would like to replace the reward model with an actual rule-based system, for example, a math problem solver, how would you ensure well-formedness for the input to the reward model? Would you see any advantages in that?
So I would refer this to a recent talk I saw by Dan Roth, where he says that um, it's easier. So we should not expect LLM to solve math. We should not expect LLM will learn math exactly the way calculators do, but we can expect LLMs to learn translate a word problem into input for calculator. Okay, so so the thing here is that converting converting natural language into a symbolic output that goes to a symbolic reward model can be done better. Instead of hoping large language models to learn all that symbolic process by itself. For example, we should not hope that LLM will learn all that symbolic math. Um, that's just unfair assumption to make. But the conversion can be a lot better. So what Dan Roth said is some kind of learning is easier than other kind of learning. Okay, so this conversion is relatively easier to learn, but solving symbolic problem on its own is much difficult. But your questions still remain valid. Like, how do we verify whether the conversion was correct or not? So I don't have a clear answer for that. So um, yeah, we need some kind. We need to rely on some kind of, again, reward models, or yeah, for that. So that is still a valid question.
Are there some good ways to avoid reasoning shortcuts?
Reasoning shortcuts. How do we define reasoning shortcut? Um,
I think, well, there is some work on that recently that maybe we'll invite here to present. But one version of it is it comes to the right answer, but through
oh,
kind of the wrong chain.
yeah. So that's what I also mentioned in the end of the two papers that I mentioned. So if the quality of answer is increasing, it does not mean that the quality of reasoning chain is also increasing. How do we avoid that? No, I think one way to do that is process reward models. But again, as long as we stay in this neural domain, Alex, there is only so much that we can do to verify um, whether the reasoning is done correctly or not. So, yeah. So we have to go to this format conversion and symbolic way. I think that's the only solution to this kind of problem.
Maybe related to that, can we say that stochastic parrots can reason just because their outputs are similar to those of real problem solving or even thinking systems for some inputs?
So I usually sorry, you're saying something?
And i.e., is it the result and not the process that makes reasoning?
Yeah. So I usually say that, can humans reason or not? So so the example that come to my mind, if we have a traffic accident and we ask both parties what happened, they both come up with their own story, right? So that's the kind of reasoning that LLMs also do. So they tend to favor whatever they have seen during the training. They just favor that. But that's how LLMs are. And if you're expecting something else from them, it's our mistake, right? Um, so in a way, yeah, it's the process. It's a process that we have, and the the process have its own biases because we gave the training, and the answer is the only thing we can verify. So yeah, the bias for answer comes from the fact that we are only verifying answer, we are not verifying anything else, right? um, so that's the issue.
Um, so let me remind everyone the format of this in general, these Neurosymbolic Wednesdays, is that it's a reading group style, and it's meant to have more in-depth, analysis that we do on each topic, as opposed to the summer school. It's more like a crash course. Um, so we sent out some reading for Asim's talk. So we'll do that as well for Luis's talk, but that's more of an overview. So you'll see survey papers and so on. But just want to say, so what's fair game for this discussion period we have after the talk is sort of both in-depth stuff if you read the paper or papers that were sent out. Totally fair game to ask something very detailed and that wasn't mentioned in the talk but was in the paper. Okay, in case any of you have that kind of question. But also, I want to encourage dumb questions, the opposite end of the spectrum, and I really think that's important because two reasons. Probably most people have your question, but nobody's saying it, and you'll help everybody. And you can use my instruction as an excuse. Alex said we could ask dumb questions, so please do. I will, from time to time, demonstrate because I like to ask dumb questions. And nobody's expected to know everything. No one can know everything in Neuro-Symbolic AI, and that's why it's so hard. Is we have to draw from principles and papers from a massive swath of areas within AI and even outside of AI. So dumb questions don't mean you're dumb. It just means you have a dumb question about this area, but in other areas you have smart questions. That's okay. So and there's the second thing is there actually are no dumb questions because it's that those are the smartest questions. It turns out those are the most fundamental questions generally. So okay, so as much as possible, I want everyone to feel this is a safe space for asking whatever. This is how we run things internally at Centaur, and I like to broaden that here. Okay. Now, let me ask a dumb question to set an example. So, in context learning, the reason, this is, as you mentioned, where this kind of thing is happening in the large reasoning models, Asim, right? So can you say a little bit, I think I find this a little mysterious, what's actually happening in context learning. And what do we know about it and what's actually happening?
So in terms of in context learning, basically there was a paper that says that it has similar effect as stochastic gradient descent has on the weights. Okay, so if we give some data, so at some level the effect is very similar. If we want to think from reasoning perspective, the input tokens are no different than the tokens that are generated by LLM in that sense from reasoning point of view. So we are, instead of asking the model to come up with the facts, we are just giving them externally to the model, and we are asking them. So we should understand that LLM is anyways generating one token at a time, right? Or in some cases like MLA, or few tokens at a time. But so all the input tokens or all the token generated by LLM should be treated exactly the same way in that sense.
Okay, very good. A few more questions. Could it be that LLMs merely reproduce the signal patterns in the data and we interpret the semantics into it? I think you've actually already given your opinion on that. Other question. Awesome talk. Thank you so much. But I disagree with the analogy. Drivers have limited perception, and that's why they come up with different interpretations. However, LLMs have almost unlimited access to the observed environment, and they still can construct reasoning on a human level.
So I totally agree. Humans have limited perception, and if like that, as we say, the truth can be different for different people. So both of them can be doing exactly correct reasoning, and yet they might differ. Similarly, LLMs seems to have unlimited kind of access to data, but they are biased toward whatever data they have seen. Okay, so For example, DeepSeek, one of the criticism that DeepSeek got is that it has some data that favors the Chinese government. Okay, so again, that kind of biases are fed through the data. If there was, I don't know for a fact, but if there was anything like that, um, so when it comes to perception, again, it seems unlimited, but especially during the fine tuning phase and especially during the alignment phase, whatever data it has seen, it has a strong bias towards that.
Okay. So one thing you mentioned is that as a kind of brittleness of these models is when irrelevant facts are put into the prompt, can cause a collapse. So you want to say more about why that happens?
Um, Sorry, Alex, can you please repeat? I was
Oh,
reading some comment here.
oh yeah. You had one point talked about something like a 65% collapse in accuracies when you put in irrelevant
Yeah.
points.
Okay. I see. What I believe is that it makes it different from the training that was done. Okay, so especially when we do just fine tuning, let's assume we have a model that has seen pre-training and it has seen a little bit of post-training on math data. Okay, what we try to do during post training is we try to give best quality data that we can to the model. Okay, very good quality, high quality question answer pairs. So if there is even a little bit of error in at inference time, the model get confused. Okay, and that is what RL is supposed to do, but it can only do so much. Like it still have some issues still remain. So it has to again do with the way we train the models. The model should not just see very high quality data, it must see some bad quality data also. And when
Mm.
it comes to bad quality, there is one good quality data, but the same example can have a lot of bad examples created in different ways, and that's what reward model RL is trying to do and trying to improve. So
So one thing I find curious is these this idea of LLMs kind of voting and sort of trying to get a higher quality signal in effect by, in some cases, asking other LLMs or having them talk to each other even, and so on. So I find this curious because if these are all kind of um, not perfect quality models, and you know if you ask if there's a danger, of course we know about things like boosting where you can have weak learners, but if you combine them they can make overall something that performs better. But on the other hand, if you ask for a consensus among a bunch of people who don't know, they all agree on the wrong answer. I mean, it doesn't necessarily help you if nobody actually knows anything.
yeah, this is a good observation, Alex. And on GSM 8K, this experiment was done. It was a paper in 2022 or 3, where they took a very weak model and they got best of 100 runs output on that model, and they found that the model is doing very good on GSM 8K. So in a way, it knew the answer. It just couldn't, in terms of precision recall. So it could recall the answer, but precision was very very low. Okay, so these models have seen similar stuff before. So if you take best of 100, best of 1,000, the models can come up with the right answer in many cases, even the weak models. Okay, the issue is that we can understand the data they have seen during supervised fine tuning a little bit what they have done at RL time, but the pre-training data, yeah, we don't know much what was done. So probably that knowledge was acquired. It's just uh, that how to bring that how to make the models output that more often. So that's what we want to do.
Uh, can you say a little bit about what's hot right now in this world of larger reasoning models? What seem to be some of the, hot topics and threads?
So first of all, when large reasoning model came, they were thought to be a game changer on their own. Right now, one major issue was they were very slow at inference time. But right now, the hot thing is agents, and agents can include large reasoning model, but it's a lot more about connecting different tools together. And of course, symbolic tools are important part of the agents. So um, connect, for example, access to good quality tools. The tool can also be coding. Okay, the tool can be math solvers, the tool can be reasoners, planners. Okay, and then um, the agentic architectures, and especially within agentic architecture, how do you incorporate good memory mechanisms, good knowledge based mechanisms, whether creating knowledge base on the fly or having some knowledge base guide your agent towards certain direction. So these are good directions to explore. LRMs on their own, unfortunately, are not mainstream right now, and we can understand, right? We want our agent to be able to use the tools that are available, not try to do everything on its own.
Okay, and part of that essentially is about getting better verifiers.
Exactly.
Um, um, or different kinds of verifiers. Um, so, one more technical question. So, at one point you talked about one of the uh, I call them tweaks or tactics is about Monte Carlo rollouts, which you know in and later in our series we're going to touch on Alpha Zero and that whole set of ideas where you have an explicit Monte Carlo tree search. How close are things coming in this uh, kind of area of work to an actual symbolic representation of the search tree?
Well, I have not used I have not seen it being used very commonly recently. There were some good papers last year that I read, but this year I have not seen many. And one of the reason is that kind of alignment is has taken over a lot of the. Even people are discussing whether SFT makes sense, so probably fine tuning makes sense or not. So, but that being said, all those approaches still remains relevant, and the message from DeepSeek was that algorithms usually win over brute force. So right now, if brute force is winning, doesn't mean that algorithms are any uh,
Mm-hmm.
better. Uh,
This is a big point. Yeah.
yeah.
Um, Another question from the audience. How can we comply with explainability requirements when LRMs are outputting incorrect explanations of their reasoning? Is this a problem that can be solved?
So this is again like we unfortunately verify the answers, right? There is no good mechanism to verify reasoning steps that are happening. So our hope always is that if answer is correct, we expect all the reasoning to be correct. Um, PR like the PRMs, you try to do that. It try to give a reward to reasoning step, but we understand again it's a neural mechanism, right? So purely in neural terms, I don't see any perfect solution to this question. So we may not be able to do exact explainability.
Oh, one more question, and then I'll do a wrap up. Do you see a way to provide semantic knowledge in LLMs? Ontologies would be a way in this regard.
So the few ways that agents tend to use is to it can be similar to RAG also. Okay, and there are some paper like reasoning bench and stuff where they try to create knowledge uh, graph as a memory. from the previous experiences of the agent. Okay, so what they try to do is they try to fetch the relevant part of the knowledge, and they feed it to LLM in a particular way. And how they do that matters a lot, and which part to fetch, that's again a question mark. So in a way, it's a new area. It's very exciting, but the way to do right now is primitive, where you just fetch and feed it to LLM and let LLM figure out what to do with it.
Okay, very good. Well, so we just did a deep dive into large reasoning models, and it was I think, worth spending a lot of time on, because this is, in some sense, the state of the art. I mean, the frontier of the battle, kind of, among LLMs. It's in. Do you think that's fair to say, Asim? In terms of the deep smartness of the models, it's here. Everyone, I think, understands that reasoning is sort of the weak point, kind of, and so trying to improve on that front is sort of where everybody is. And so exactly how that's being pursued in the world of LLMs, which is kind of the mainstream, or at least is where the most kind of resources are being put in the world, primarily by big tech companies. But so we watch this space closely, and what is going on there. So, and we have someone working right at the front lines. Asim just gave us a peek into that. So thanks so much, Asim. Next up, for those of you, and this is, I think, a great motivation for, why Neuro-Symbolic. It's one of the reasons. Next up, Luis will give us a sort of broad view of what is Neuro-Symbolic, what are some of the threads within it, and that'll set us up for a next kind of sequence of talks. Let me also ask, of course, we do our best to kind of curate a good sequence and set of topics for the community, but you can help us. So anything you want, you think, especially in suggesting talks, because they're always great works. I'm always afraid I've missed something, even though I read a lot. I have 1,700 open tabs in my browser, all sorts of papers. So, but missing something is what I'd like for us not to do. So, so please, if you find things that you really want to hear about, and you want us to invite the speaker, please let us know. Or if you want to volunteer to be a speaker, let us know. You can also present somebody else's paper, in particular an older paper that's a classic or an influential one, as Asim did just now. So presented a little bit about the sequence of works from DeepSeek. All right, so hope to hear from everyone on Discord, and thanks for joining us. See you next Wednesday.